Due to COVID disrupting students' education for the 2022 summer GCSE exams, the exam boards have released an advanced notice article that gives an insight into what will be on the exams this year. I'm sure your teachers have shown you this article already. In this version of the advanced notice article, I'm going to show you anything in green is definitely going to be on the exam. Anything in yellow may be on the exam in a small way, and anything in red will not be on the exam. In this video, I'll go over the green and yellow areas to help you prepare for the Combined Physics Foundation Paper 2 exam. Here's SP8, Energy, Forces Doing Work. You're supposed to be able to describe the changes involved in the way energy is stored when systems change. So what that means, when a system changes, that could be a car braking, which would be kinetic energy stored in the car getting turned into heat energy stored in the brakes. It could be a light bulb, where there'll be electrical energy getting turned into light and heat energy. Draw and interpret diagrams to represent energy transfers. So an energy transfer diagram, for example, for a bulb would be electrical energy going in and it's getting converted into light, useful energy, and heat, which is wasted energy. Explain that where there are energy transfers in a closed system, there is no net change to the total energy in that system. What that basically means is what goes in must come out. So it's the law of conservation of energy. For example, if 200 joules of electrical energy goes in, 200 joules needs to come out. Now, not all of the energy that comes out will be useful. There's only 80 joules here that's actually useful. 120 joules is being wasted. But it's still there. 200 went in and 200 came out. You just can't use this wasted energy for any further useful energy transfers. Identify the different ways that the energy of a system can be changed through work done by forces, which basically means mechanical work. And that's when a force moves an object through a distance. Using this equation, work done equals force times by distance. Electrical equipment. So electrical work, for example, could be charges moving due to a potential difference or voltage. And heating, well, that would be something like heat energy transferring from one place or object to another due to a temperature difference, which can be caused either electrically, but from current, or by chemical reaction, for example, burning a fuel. Describe how to measure the work done by a force and understand that energy transferred in joules is equal to work done. There we go. Energy transferred is equal to work done. Now remember, work done is force times by distance if you're talking about it in a mechanical sense. In other words, when you're moving things. Recall and use the equation work done equals force times by distance. So there it is there, W equals F times by D. But you could also see it as E equals F times by D, because remember, work done equals energy transferred. So it's just a case of you putting the numbers in. Describe and calculate the changes in energy involved when a system is changed by work done by forces. So in other words, it's just energy transferred equals force times by distance. So they'll just give you the numbers, you've just got to pop them into your calculator. Recall and use the equation to calculate the change in gravitational potential energy. So again, it's just this equation, and you've just got to pop the numbers in. So the change in gravitational potential energy equals mass times by gravity times by change in height. Recall and use the equation to calculate the amount of energy associated with a moving object. In other words, you've got to be able to calculate kinetic energy using this equation. Kinetic energy equals a half times by the mass times by the velocity squared. Make sure you square the velocity first before you do anything else. Explain using examples how in all system changes energy is dissipated so that it is stored in less useful ways. In other words, you always lose energy as heat and sound, and it goes to the surroundings. And that's usually because of friction. Explain that mechanical processes become wasteful when they cause a rise in temperature, so dissipating energy in heating the surroundings. Well, that's what I've just said there. Mechanical processes, in other words, it's friction. When objects move and rub, it causes heat and sound, which dissipates to the surroundings. Try to memorise that statement there. It could be worth up to 3 marks. Define power as the rate at which energy is transferred and use examples to explain this definition. For example, that ties straight in with this equation. The power equals energy transferred over time. Power is measured in watts and energy is measured in joules and time is measured in seconds. So 1 watt is equal to 1 joule per second. And there we go there. Recall that 1 watt is equal to 1 joule per second. And recall and use the equation for efficiency. So efficiency equals useful energy transferred by the device divided by the total energy supplied to the device. For example, a bulb. If we put 200 joules of electrical energy in and 80 joules gets turned into useful light and we've wasted 120 joules, to get the efficiency you do the useful energy that came out divided by the total energy that you had to put in. So in other words, 80 joules of light energy came out, we had to put 200 joules in, 80 over 200 comes out as 0.4. Now if the examiner wanted you to express it as a percentage, multiply that by 100 and it comes out as 40% in this case. Unit SP9, forces and their effects. There's only one thing that we need to learn here, and that's 9.10. Explain ways of reducing unwanted energy transfer through lubrication. So what they're talking about here is when you've got moving objects, you're going to have friction because the objects are rubbing against each other. So if you lubricate the surface, you'll create a little bit of space where the objects can move over each other easier. Now, how do you tell the examiner that? You say, apply oil to the moving objects. For example, a gearbox or a bike chain are moving objects. That'll reduce friction, which reduces heat and sound from being produced, which is wasted energy. Because you often get friction in motors and things like that, and you don't want the motor getting hot. SP10, electricity and circuits. 10.1. Describe the structure of the atom limited to the position, mass and charge of protons, neutrons and electrons. In other words, you've got to know where each of these particles are in the atom, what their mass is and what their charge is. So the proton is found in the nucleus. It's got a mass of 1 and a charge of +1. The neutron is also found in the nucleus. It's got a mass of 1 and a charge of 0. Neutron is neutral. Proton was positive. And the electron is found in shells that orbit the nucleus. Its mass is approximately 2,000 times lighter than the proton and the neutron. It's 1 over 1,835 if you want to be precise. And the charge is -1. 10.2. Draw and use electric circuit diagrams representing them with the conventions of positive and negative terminals and the symbols that represent all of these things over here. So the cell, the positive side of the cell is the large side. What I tell my students is if you add something, it gets bigger. So the big side is the positive side and the smaller side is the negative side. And that goes for the battery as well. So we're only interested in the outermost part of the battery there and then the outermost part of the battery there. So that was big, so that's the positive side of the battery, and that was small, so that's the negative side. Closed switch, Harry Potter's glasses. I've got a nice video that goes over all of these. Voltmeter is a circle with a V, it measures voltage. Ammeter is a circle with an A, it measures current. Open switch is Harry Potter's broken glasses. Resistor is just a box. Variable resistor is just a box with an arrow through. I like to think of the arrow there as like an upside down V, V for variable. A lamp can be represented either as an X-Man badge or as an omega sign inside the circle. The motor is a circle with an M. Diode is D, I, O, first three letters of diode. A thermistor is a resistor with a thermometer through it, or it looks like a golf club. An LDR is a light dependent resistor, so that's a resistor in a big circle to keep it dry because it goes on top of lampposts. And here's the sun shining down on it. And an LED is a light emitting diode, so it's a diode D-I-O that gives off light. 10.3. Describe the differences between series and parallel circuits. A series circuit has only one loop. The parallel circuit has more than one loop. Recall that a voltmeter is connected in parallel with a component to measure the potential difference of voltage in volts across it. So there you go, we're trying to measure the voltage of that bulb. So you put your voltmeter in parallel across the bulb. 10.5. Explain that potential difference. Voltage is the energy transferred per unit charge passed, and hence that the volt is a joule per coulomb. So in other words, it's basically this equation here. Voltage equals energy over charge, which is down here. So, but rearranged, E equals Q times by V. So energy, EastEnders, is the Queen Vic. Energy, charge, voltage. You're very often asked for an alternative unit for a volt, so make sure you memorize 1 volt is the same as 1 joule per coulomb. 1 volt is 1 joule per coulomb. Recall that an ammeter is connected in series with a component to measure the current in amps. So here we go, there's the ammeter in series, so one thing after another. Doesn't matter if the ammeter is before or after the other component. 10.8. Explain that an electric current as the rate of flow of charge, and the current in metals is a flow of electrons. So current is how much charge you've got divided by time. In other words, it's the rate of flow of charge. 10.9. Recall and use the equation charge equals current times by time. The way I like to remember that is when you're charging your mobile phone, you need to put a current into your battery, so that's why you plug it into the wall and you leave it plugged in for a certain amount of time. The more time you leave it plugged in for, and as long as there's a big current going in, then your mobile phone will get charged. And 10.10, describe that when a closed circuit includes a source of potential difference, there will be a current in the circuit. So a closed circuit just means a complete loop, and what we're basically saying is it's at the potential difference of voltage that creates or causes the current. So if you've got no voltage, you won't get any current. So what came first, the chicken or the egg? We're not sure, but what comes first, the voltage or the current? It's the voltage. 10.11. Recall that current is conserved at a junction in a circuit. All that means is that whatever current goes into a junction must come out of the junction, which is Kirchhoff's law. So you can see 4 amps comes into the junction and 4 amps is leaving the junction by 2 different paths. In this particular case, the resistance along each of these paths must be the same because the current split 50-50. And as the current gets to this junction, 2 amps plus 2 amps goes back to the 4 amps. 10.12. Explain how changing the resistance in a circuit changes the current and how this can be achieved using a variable resistor. So variable resistors are used to adjust the size of the current. If you've got a large resistor, it makes the current small, and if you've got a small resistor, it makes the current big because it lets the current flow without stopping it as much. 10.13. Recall and use the equation. This is Ohm's law. It's voltage equals current times by resistance. So they'll give you the numbers and you've just got to pop them in. That should be easy marks. 10.14. Explain why, if two resistors are in series, so that means one after the other, the net resistance is increased, whereas with two resistors in parallel, the net resistance is decreased. So if you've got resistors in series, there's only one path for the current to travel down, so the current needs to go through both resistors. So 5 ohms and 5 ohms would act like a 10 ohm resistor. You just add them together. Whereas with resistors in parallel, there's two paths to travel down. So some of the current can come this way and some of the current can go that way. Because there's two paths, it allows the current to stay big, and we can see from this equation here, R equals V over I. If the current is big on the bottom, that makes the resistance small. Which leads us on to 10.15. You should be able to calculate currents, voltages and resistances in series circuits. So they'll just give you two of the numbers and you've got to work out the third. And that's the equations rearranged for you. 10.16. Explain the design and construction of series circuits for testing and measuring. So this is your standard test circuit. It allows us to measure the current using the ammeter and measure the voltage using the voltmeter. And then to get the resistance of the component, you just do the voltage divided by the current, V over I. If you've got to get multiple readings, pop a variable resistor in, and that'll allow you to change the currents and their corresponding voltages and get you multiple readings. If, for example, you wanted to plot a graph. We don't need to know any of this stuff, so we'll jump straight on to 10.22. Recall that when there is an electric current in a resistor, there is an energy transfer which heats the resistor. So for 1 mark in an exam, you just say that it's current in a resistor that makes the resistor get hot. So you would actually lose some of your electrical energy as heat energy. 10.23. Explain that electrical energy is dissipated as thermal energy in the surroundings when an electrical current does work against the electrical resistance. In other words, as I've just said, resistors get hot when current passes through and the heat, the thermal energy, goes to the surroundings. You get about 3 different marks for seeing that. 10.24. Explain the energy transfer in 10.22 above as the result of collisions between electrons and the ions in the lattice. So, the reason why resistors get hot is that because as the current, the little electrons, are flowing through the metal, there are collisions between the electrons and the copper ions, perhaps, that make up the wire. And all of those little collisions cause a little bit of friction, and friction causes heat. So you'll get anything up to 3 marks for seeing that. 10.25. Explain ways of reducing unwanted energy transfer through low resistance wires. In other words, if they say how can you lose less heat in a wire, you say use low resistance wires. Low resistance wires are short and thick. So the shorter the wire and the thicker the wire, generally it has lower resistance. 10.26. Describe the advantages and disadvantages of the heating effect of an electric current. Well, heating effect of current is an advantage, it's good, if you want the device to actually get hot. For example, if you're using a heater or a hairdryer, the electrical energy will get turned into heat, which is good because that's what you want. or it's a disadvantage in any device not designed to get hot. For example, a phone or a PC. If you're putting electrical energy in and that electrical energy is turned into heat energy and you don't want it, then that's clearly a disadvantage. You could end up breaking your PC or phone because it overheats. 10.27. Use the equation energy transferred equals current times by voltage times by time. So E equals IVT. I prefer E equals ITV because in England ITV is a TV channel and I say Emmerdale is on ITV. Not that I watch it, but I do know that that is a TV programme that exists. So that helps me to remember that. And in your exam you'll just be given the numbers and you've got to pop them in. So that should be easy marks. 10.28. Describe power as the energy transferred per second and know that it's measured in watts. So for 1 mark in an exam, you just literally say that power is the energy transferred per second. For another mark, you say it's measured in watts. And you've got to know that 1 watt is 1 joule per second. And that ties in with 10.29. So power equals energy transferred over time. So that'll be how many joules you use per second. 10.30. Explain how the power transfer in any circuit device is related to the potential difference across it and the current in it. In other words, power equals current times by voltage. Now, you'll also be given an equation called power equals current squared times by resistance. 10.32. Describe how in different domestic devices energy is transferred from batteries and the AC mains to the energy of motors and heating devices. So what I've done is I've showed you an energy transfer diagram to show that happening. So in a motor, you'd have chemical energy in the battery getting turned into useful kinetic energy, because that's what you want a motor to do. You want it to move, you want it to spin. And obviously wasted energy will be heat and sound because of friction. Another transfer diagram is electrical energy in the AC mains inside a motor. Again, the useful will be kinetic energy and the wasted will be heat and sound. And in a heater, if you're using battery, once again it will be the chemical energy in the battery that's going to heat energy. I haven't done any wasted energy this time because even the wasted energy will be heat energy, which will be useful as long as it goes to the right area. And if you're using the AC mains, then it would be electrical energy turning into heat energy rather than chemical energy. 10.33. Explain the difference between direct and alternating voltage. So direct voltage is a steady voltage and it comes from batteries and cells. I've showed you a graph here. So the voltage would stay steady over time. And alternating voltage is when the voltage alternates from positive to negative, and that comes from the mains. And if they wanted to show you a graph, this is what it would look like. Positive, go back to 0, negative, back to 0, positive, up and down like that. So you can see the voltage is alternating, backwards and forwards, positive and negative. 10.34. Describe direct current, DC, as movement of charge in one direction only. So 1 mark for that. And recall that cells and batteries supply direct current. So another mark for that. And this is what the picture would look like. So direct current coming from the battery, just going in one direction. I've showed you it as conventional current, which is flowing from the positive to the negative terminal. So from the positive to the negative terminal. 10.35. Describe that in alternating current, AC, the movement of charge changes directions. So in other words, the charges are electrons and they'll go backwards and forwards, alternating. That's why we call it alternating current. So from AC mains, the current flows forward for 1/50th of a second, like that, and then it reverses and flows backwards for 1/50th of a second. And obviously it's doing that, changing from forwards, backwards, 50 times in a second, which means it's a frequency of 50 Hertz. Which takes us to the next statement, 10.36. Recall that in the UK, the domestic supply is AC at a frequency of 50 Hertz. So 1 mark for saying the mains is AC, and 1 mark for saying the frequency is 50 Hertz, and another mark for saying that the voltage is about 230 volts. So 50 Hertz means that the direction is changing 50 times per second, as in these pictures here. 10.37. Explain the difference in function between the live and the neutral mains input wires. So the live wire takes the voltage in to the device, and it takes the current in, and the neutral wire completes the circuit so that it's a complete loop, otherwise current wouldn't be able to flow. So the neutral wire takes the current out, away from the device. The live wire has got a voltage of 230 volts, and the neutral wire has got 0 volts. That's why they call it the neutral. 10.38. Explain the function of an earth wire and of fuses or circuit breakers in ensuring safety. Well, for 1 mark, an earth wire and a fuse is used for safety, and so is a circuit breaker. Now, the earth wire stops an appliance's metal casing from becoming live. You can get 1 mark for saying that. I've got a nice little video all to do with earth wire, fuses and circuit breakers on my channel. Have a little look if you need more guidance. Fuses and circuit breakers are connected to the live wire. So if there's a surge in current, the fuse melts or the circuit breaker trips, which puts a break or a gap in the circuit, turning it off, which prevents electric shocks and fires. So that's everything that you need to know to pick up 3 marks. 10.39. Explain why switches and fuses should be connected in the live wire of a domestic circuit. Well, that's because the live wire brings the voltage in to the device. If the switch was connected to the neutral wire, the device would still be live even when the switch was off. So if you had the switch in this wire here, the neutral wire, then the live wire would still be bringing the current in. So even if you switch this on and off, this would still be connected. So you need to put the switch in the live wire so that the current gets stopped before it gets to the device. 10.40. Recall the potential differences between the live, neutral and earth mains wires. So in other words, tell us what the voltage is. Well, the voltage of the live wire is 230 volts, the neutral is 0 volts, and the earth is also 0 volts. 3 marks for them. 10.41. Explain the dangers of providing any connection between the live wire and earth. Well, current only flows through the earth wire when there's a fault. A fault could cause a fire or electric shock. So the earth wire should stop this from happening. So that's the dangers. 10.42. Describe with examples the relationship between the power ratings for domestic electrical appliances and the changes in stored energy when they are in use. Well, higher power would equal more energy transferred per second. So that's the relationship between the power rating and how much energy it changes per second or stores. So if you've got 50 watts, that means it'll store or use 50 joules per second. If it's 100 watts, that means it uses 100 joules per second. Unit SP12, Magnetism and the motor effect. Recall that, unlike magnetic poles attract, just like that, and like magnetic poles repel. So a north repels a north, a south repels a south, and a north and a south will attract. Describe the uses of permanent and temporary magnetic materials, including cobalt, steel, iron and nickel. Well, the first thing is, make sure you know that they are the 4 magnetic materials that you'll need to talk about at GCSE. And the uses, well, the uses of permanent magnets. For 1 mark, you use them in a fridge door, or for separating recycling, like steel cans from aluminium cans. And uses of temporary magnets could be maglev trains, which is magnetic levitation trains, and electromagnetic cranes found in junkyards and places like that, where they've got to move metal from one place to another, and they use temporary magnets. What they mean by that is electromagnets, so they can turn them on and off. Explain the difference between permanent and induced magnets. So, a permanent magnet is always magnetic. Well, that's easy, isn't it? It's always got a magnetic field around it. But an induced magnet, they are only magnetic when in another magnet's magnetic field. So, if you just had a piece of iron, it wouldn't have its own magnetic field. But if you put that piece of iron next to a magnet, it'll gain its own magnetic field from the permanent magnet. So the permanent magnet goes north-south. The induced magnet would also be north-south. So make sure you do the north next to the south. I've got videos on my YouTube channel in all these different playlists if ever you need any extra help. Check out the full videos. Describe the shape and direction of the magnetic field around bar magnets and for a uniform field, and relate the strength of the field to the concentration of the lines. Now that's what I've just explained with the electric fields. So with a bar magnet, you've got the lines are closest where the poles are. So the magnetic field is strong here because the lines are close together, exactly the same here. And the magnetic field is weak on the outer edges over there and over here, further from the magnet. And that's because the further away from the magnet you get, the weaker the magnetic field is. We represent the strength of the magnetic field by the lines. And the magnetic fields come out of the North Pole and go into the South Pole. Describe the shape and direction of the magnetic field around a bar magnet and for a uniform field. So for a uniform field, you'd have this plate here and this plate here, which are parallel to each other. And you'd have a uniform magnetic field lines equally spaced out going from the north to the south. Notice around the edges here, it's not quite uniform, so it's just this part right in the middle between the 2 poles. Describe the use of plotting compasses to show the shape and direction of the field of a magnet and the Earth's magnetic field. So the field around a magnet, what you basically do is just put plotting compasses all over the place. You can see I've strategically placed them to show that the field comes out of the North Pole and goes into the south. So these compasses here would show the shape and direction of a magnetic field. And what you do is you just, whichever way the compass is pointing, draw a little arrow coming out of the compass on the paper next to it. Little arrows coming out like that. And then you just connect all those arrows together there, connect all these arrows together there, and just do the same coming down that way. I've got a video that shows you how to do it if you don't understand what I'm talking about. And the Earth, where the North Pole is and the South Pole is, there's exactly the same field coming out of the Earth. But obviously it's not horizontal like that. The poles would be vertical. Explain how the behaviour of a magnetic compass is related to evidence that the core of the Earth must be magnetic. Well, basically, a compass points to Earth's North Pole. That'll get you 2 marks. Unit SP13, Electromagnetic Induction. You can see for the foundation candidates, none of this unit at all should be on, if the advice from the exam board is accurate. So you don't need to know any of that stuff. SP14, particle model. This is probably going to be on the exam. This will be on the exam. These probably won't, or if they are, just 1 mark. Use a simple kinetic theory model to explain the different states of matter. So remember, that's solids, liquids and gases, in terms of the movement and arrangement of particles. So here's your 3 states of matter: solid, liquid and gas. Now your particle arrangement, you say that the solid is in nice neat rows, you get fixed volume, fixed shape, and the particles are very close together. As a result, the density will be very high. And how do the particles move? Well, by vibration only, because they're bonded together. The particles in a liquid are irregular, which means they're all over the place. They've still got a fixed volume, but they don't have a fixed shape. They'll fill the shape of the container. And the particles are close together as opposed to very close in the solids. How do they move? Well, the particles move slow and randomly. Particles in a gas are irregular, so it means they're all over the place. Not a fixed volume this time. A gas will fill the volume of the room. It's not a fixed shape either, and the particles are far apart. How do the particles move? Rapid and random. Or if you don't like the word rapid, just say fast and random. Recall and use the equation. Density equals mass divided by volume. So we use a wiggly P for density, M for mass, V for volume. Core practical. Investigate the densities of solids and liquids. Now this is going to be one of the core practicals, so it's worth 6 marks. So let's have a good look at this. So if you're going to investigate the density of a regular solid, for example a cube, well, always base your explanation on the calculation. So to get the density of whatever, you need to know the mass and the volume. Tell the examiner you'll use this equation. Tell the examiner that to get the mass, you'll use a mass top pan balance. And to get the volume, because it's a regular shape, you just do the height times by the width times by the depth. So just use a ruler. In order to get the density of an irregular solid, so that means like an odd shaped solid, again, tell the examiner you're going to use density equals mass over volume. Now you can get the mass once again just by using a mass top pan balance, so it doesn't matter that it's a funny shape, you can still put it on the top and you'll get the mass. However, this time to get the volume, what you'll need to do is take a measuring cylinder, so tell the examiner that, and fill it up with water to say halfway, and then plop the shape into the water and the water will rise. Now if we say the volume at first was volume 1 and the volume after you've put the object in is volume 2, then to get the volume of the irregular shaped solid, just do volume 2 take away volume 1. And that will also get you anything up to 6 marks. Now if you're going to get the density of a liquid, well, get a measuring cylinder, put it on top of the mass top pan balance, and then press the tare button to take it back to 0. When you put your liquid into the measuring cylinder, the mass top pan balance will just tell you how much mass of liquid there is. And the beauty of this is at the same time, the measuring cylinder will also tell you the volume. So you just get the mass and the volume by using the mass top pan balance using that technique. Explain the differences in density between the different states of matter in terms of the arrangements of the atoms or molecules. So specifically to do with the density, solids, the density is very high, liquid density is high, and gas density is low. So with the exception of water and ice, most solids are more dense than their liquid variant. And as they turn into a gas, so that's another physical change, generally the particles spread out even more. Describe that when substances melt, freeze, evaporate, boil, condense or sublimate, mass is conserved. So that just means the mass that goes in equals the mass that comes out, and that these physical changes differ from some chemical changes because the material recovers its original properties if the change is reversed. So sometimes if you have a chemical change, the properties will be totally different and you can't reverse it. But if you're just changing the state of matter, that's just a physical change. And if you reverse the change, you'll get the same properties back. So if we start with solid, going to a liquid, going to a gas. A solid melts and turns into a liquid, and then it evaporates or boils and turns into a gas. If you cool the gas, it'll condense to form a liquid. Once you've got the liquid and you cool it, it'll freeze to a solid. When it's a solid, it doesn't have much energy. When it's a liquid, it's got more energy. And when it's a gas, it's got high energy. And sublimate is when you turn from a solid directly into a gas without going into the liquid state of matter. Explain how heating a system will change the energy stored within the system and raise its temperature or produce changes of state. So that's what I've just said there. The solid has got a low amount of energy, a liquid's got medium amount of energy, gas has got a high amount of energy. You know, you could be asked that in your exam, you get 1 mark for each of those things. Define the terms specific heat capacity and specific latent heat and explain the difference between them. So remember, it's only worth 1 mark. Well, specific heat capacity is the amount of energy needed to raise the temperature of 1 kilogram of a substance by 1 degree C. Specific latent heat for 1 mark in an exam, it's the amount of energy needed to change 1 kilogram of a substance from one state to another without changing its temperature. In other words, specific latent heat is what you use if there's a change of state. Specific heat capacity is what you use as you're heating one state and it's getting close to either the melting point or the boiling point. Use the equation. Change in thermal energy Q equals the mass times by specific heat capacity times by the change in temperature. Now, you'll have to rearrange that sometimes in order to find the specific heat capacity. So if you know how much energy you're putting into a liquid or a solid, and you know the mass of the liquid or solid and how much it's changed its temperature by, then you'll be able to work out what the specific heat capacity of the solid or the liquid is. Use the equation Q equals M times by L. So that's the amount of thermal energy needed for a change of state. And that's the mass times by the specific latent heat. Explain ways of reducing unwanted energy transfer through thermal insulation. In other words, wrap up something in foam or put a lid on it if you don't want to waste thermal energy from that thing. 1 mark for each of those things. Now here we go, here's the 6 marker, this is your core practical. So this will definitely be on the exam. Investigate the properties of water by determining the specific heat capacity of water and obtaining a temperature time graph for melting ice. So here's how to determine the specific heat capacity of water. You'd need to fill a container with a known mass of water. And for another mark, measure the starting temperature of the water. For your 3rd mark, use a heater connected to a joule meter to heat the water. Measure the final temperature of the water. Measure the amount of heat energy used. And then calculate the specific heat capacity by using C equals Q divided by mass times by temperature change. The temperature change will be the final temperature. Take away the temperature at the start. I've got a nice little video all to do with that. Definitely recommend you watch it. Obtaining a temperature time graph for melting ice. Right, what you do is you tell the examiner that you would heat some crushed ice. You'd record the temperature and the time. So say heated for 10 minutes, record the temperature over the 10 minutes. And then use those results to plot your temperature time graph. Now what you should find is when it's ice, it'll start to heat up and heat up. Now once it changes from ice, which is a solid, into water, which is a liquid, during the melting process, you should end up with a flat part of the graph. It's what we call a plateau. And that's because it's changing state. Now you're still putting energy in because you're still heating it. So you say, well, where's that energy gone? Because the temperature's not going up. The energy is being used to break bonds, turning it from a solid into a liquid. Once it's fully turned into a liquid, then the temperature will continue to go up. Once it reaches a change of state again and changes from a liquid into a gas, once again you'll end up getting a flat part, which is your plateau. Now these plateaus, because there's no change in temperature, that's when you'd use this equation here. Q equals m times by L. You'll notice there's not a change of temperature involved when you're using the specific latent heat as it's changing state. As it's changing the temperature, and this section here and this section here, that's when you would use the equation for specific heat capacity, which does involve the change of temperature in the calculation. Again, if you're not sure about that, check out my video from the SP14 playlist. Explain the pressure of a gas in terms of its motion of its particles. You just need to say that the pressure of the gas is because of the motion of the particles. Pressure is caused by collision of particles. For 1 mark. Explain the effect of changing the temperature of a gas on the velocity of its particles and hence the pressure. Well, if you increase the temperature, that's going to increase the velocity of the particles and that's going to increase the pressure. And it does say for a fixed mass of gas at a constant volume. Describe the term absolute zero minus 273 degrees C in terms of the lack of movement of particles. So just make sure you know that the coldest temperature you can ever get is called absolute zero, and it's at minus 273 degrees C. And at that point, there's no movement of the particles, or it's very, very minimal. And therefore, if the velocity is zero of the particles, then there'll be no pressure either. It's only worth 1 mark though. Convert between Kelvin and Celsius scales. So if it does ask you to do this, to convert degrees Celsius into kelvins, take the degrees Celsius and add 273 to it. For example, if you've got 27 degrees C, that'll actually be 300 Kelvin. And to go from kelvins into degrees Cs, you take 273 away. So if you had 300 Kelvin, that's actually just 27 degrees C. Unit SP15, Forces and Matter. Neither the foundation nor the higher candidates need to know anything from this unit. So that's the end of the video. So I hope that helped you. Remember, I've got 24 years of experience. I've seen lots of exam papers, teaching physics for 24 years. And the way that I've explained each of the specification references is trying to keep it as simple as I can, and you tell the examiners what I've said and you should be able to pick up a lot of marks. So work hard, be nice, and bye for now.